We're still on the first one of 13, and we'll get that finished today. At least that's my goal. And then we'll move on to the last section. So there are two questions involving calculating the test statistic. And these two questions are numbers 10 and 11. And I'm just going there right now to make sure I've got similar numbers. Okay, so the test statistic, they are calling it, or one of the other four names have got, the t-score. You get it by this formula. The sample mean, take away a guy called mu naught, divided by the standard error of the sample mean. X bar is the sample mean. Mu naught is called the null value. It's a bit like P naught. Whenever you have a hypothesis, isn't there always a mu equals 20, a mu equals 100, a mu equals something? That number, that something, is the guy that goes there. And then the standard error is given by this formula, the square root of the standard deviation over n. And if you put that package together, you will be able to calculate the t-score. So the first one I'm going to be doing is question 10a. In their story, the null hypothesis was 55. They told us that X bar was 75. They told us S, the standard deviation, was 80. And finally, they told us that N is 121. So as long as I know all these guys, I am good to go. So the test statistic, the T guy, is X bar, take away mu naught over the standard error of X bar. Well, that guy there, we call that guy mu naught. To get the standard error, I do, and I just put that in the wrong place. My square, let's write it so it doesn't look as weird as it should. Yeah, my square root was in the wrong place. So it's S over the square root of n. So it's 80 over the square root of 121, which I'm going to turn into a decimal. So 80 divided by the square root of 121 is 7.27. And let's check how much accuracy. Okay, so they want 2 decimal places, so I'll make that a little bit more accurate. So I've got all the numbers now. The mean of the sample was 75. The mu naught value was 55. And the standard error was 7.2727. And because they wanted the answer to 2 decimal places, I made sure that was a couple of decimal places extra just because of rounding off errors. So on our calculator, put a bracket. I'll do 75, take away 55, and then divide it by 7.2727, hit enter, and the answer I get is 2.75. Are you comfortable about those questions that ask you to find the t-score? As long as you know these numbers, you can get the standard error, and then you can put them all together, and you got your t-score. Are we good?
That was just the T statistic in salt. Yeah.
That would have been the T statistic in salt if they gave you just a little bit more information. So what information was missing? They forgot to tell you whether the alternate was bigger than or less than, right? But you could have pretended it was bigger than and you would have got this. Now, if you go to question 11, that's the other one like this. They give you the null hypothesis is 260. They give you X bar, which is 302, and they tell you the standard error. So they actually make your life a lot easier than it needs to be, because There we go. And it's 302. That number there is mu0. So take away 260. And since you told me the standard error is 6, I don't even care about that number because I don't even use it. So on my calculator, 302, take away 260. There we go. Divided by 6. And the answer I got for this one is 7. So if they don't tell you the standard error, but they give you these two, you can find the standard error. If they do tell you the standard error, I don't care how big the sample size is, they've already used it when they calculated this. So that was an example of a piece of information you didn't really need. So those were two little afterthoughts. I want to make sure that we're clear on those. So the main part of today is now about to begin, where we're going to be using salt for the entire hypothesis test from 12 to 17. So I'm going to nip over here and I'm going to have to do a few alterations. If you can bear with me just for a little while. I'm going to go into student view. Oh, come on. There we go. Open student view. And close. Okay, I should be able to do this now. So I want to try and make it a little bit more like how you see the questions, because my version's a little bit different, right? So yours is probably going to look like that, isn't it? That's basically what your web would look like. And we're still on the top one, which is what we're going to work on today. I'll click on that. And, oh, there's my name in print. I'm famous. Okay. And the first question we're going to look at is question 12. So we're being asked just to find the p-value. So they haven't got any story. All they've given is all the stuff you need to know here, right? And a 29 and a 2.1. So in this question here, they don't tell us what the numbers are. They just say it's equal to or bigger than, but that's enough to get the p-value. So we're going to use salt in a slightly different way. I'm going to, okay, I better write these numbers down because sometimes when you hit it, the guy underneath disappears. So 29 was the sample size and the t-value is 2.1. So let's see how that works. Click on that. Oh, cool. Now, when you hit salt, you see it took you to distribution calculations, right? Now I'm going to go here and I'm going to go T distribution. And my sample had 29 numbers in it. How many degrees of freedom is 29 numbers?
28.
28. Doesn't make a big difference, but it will make your answer slightly different, right? So you have to make sure it's 28 or else the WebAssign won't like you. Now, we were looking at a bigger than, that's right-tailed, right? Hypothesis test. And the number that it had to be bigger than was a t-value of 2.10. So 29 gave me 28. Bigger than meant go to the right. And I wish they'd put a T there, but they don't. But pretend it says T. Bigger than 2.9. That fella is the p-value. Right? This guy down here. So I'm going to copy it. I'm going to go over here. I'm going to put it in. And if we look at our picture, didn't our picture look like that guy? And so I should, where did I put my, oh, here we go, submit answer. And I just remembered something. Oh, Oh, they are being generous, or maybe it's just because it's me. Didn't they ask the answer in 4 decimal places? And if you count that, isn't that 5? So I'm going to round it off to 4 and submit my answer. Yeah, just want to be perfect, right? If it says 2, you should really do 2, even if it says you're right with 4. You want to be 100% right. Okay, are we cool with that one?
What was the part we skipped?
You're very quiet. You want to? I'm not sure why. Whoever just spoke, I can't really hear you. Question?
We skipped a part in question 12. I was just curious what it was.
Oh, I'm not sure what we switched. We used distribution calculation for this one.
Yeah, in the question we skipped the middle portion of the question. And
I didn't even know that. Let me find the middle portion of the question. Oh, there's a part B. I see her. Part B is just another one of the same questions, right? So let's do it since it's here. This sample is 29 again. We're doing a greater than again. And the t-score that we're going to use is negative 2.10. Okay, I should be able to do all of that. So the only difference in that one is that this number was negative 2.10. And so that guy is our p-value. So let's check why that's the case. 29 t-value bigger than means right tail, right? And the answer we got for the p-value was ridiculously big. And let's check it. There you go.
Okay, and for my number 11, I did the mean minus the mu note divided by standard error, and I got a different answer than what I got off of when I did it on salt.
Okay, so did you take 292 first, take away the 260, and then divide it by 4? Right.
My mean is 258, and the mu note is 240, and my standard error is 6.
So 250, take away 240, and your guy was 6.
258.
Okay, let me go to the white screen and I'll write down that calculation and we'll see if we can make it happen then. It sounds to me like it might just simply be a calculation thing. Okay, so what was the value of X bar in your question?
258.
And the mu naught guy?
240.
And the standard error guy?
6.
So in your case, it's going to be 18 divided by 6, which is 3.
Oh, maybe I did do it wrong.
Right, now the mistake you're likely to make is not having brackets around the top 2 numbers. So 258, take away 240, make sure the brackets around them. Then when you divide by 6, you get 3. If you don't put brackets around them, it might look okay when you see it on the screen, but the order of calculations will give you a really totally different answer. You see, without the brackets, it's 218.
Yeah, perfect. Thank you.
No problem. So let's return to our next question then. I didn't notice I missed that second one, so thanks for catching that. Okay, here we have the whole kit and caboodle, the whole story. I think I did this one. Did we do 13 last time? It has a familiarity about it. No? It's the PSI and the tires. I think we did this one.
Yeah.
Or at least if we didn't, there might be another one just like it, because they seem to have the same story that they keep repeating. And tires story seems to be one of them.
You did. There were 2 tire stories. You technically did 13. You just didn't do it on the homework. You just took the numbers from it.
Ah, okay. So let's just do this one as from brand new then, right? So on an earlier exercise, how many cars have a tire pressure, right? So it's the same tire pressure story. I won't read through that. So what did they do? They took 65 in your sample. Right, I'm writing this down. So N equals 65. Got that? They wanted to know whether drivers on average have too little drive, right? So they want to prove that it's less than 32. And suppose it's conducted and the standard deviation was 29. So write that down, 29.3. Well, 29.3 was the mean and the standard deviation was 3. Okay, I got all the numbers now. Okay, so in this story, you might have to go back a couple of times if you miss something. I might end up doing it myself. We'll hit the use salt button and it's on inferential statistics and it's on one sample. And the sample mean was 29.3 and the standard deviation was 3 and the sample size, so I don't need to change anybody, is still 65. I then make sure it's hypothesis test. That guy should be 32 and we're trying to prove that people tend to be less than that. So be comfortable about one sample, the sample mean, the sample standard deviation, and the sample size. That's H naught says the mean should be 32. We're trying to prove is it less, right? So that's all the pieces. So when I hit generate results, can you see it? It actually does your null and alternate. Okay, they call it H naught and H1, but HA is the same guy, right? 32. And so I want a test statistic, which is this number. Which is going to go there. And I also want the p-value. Which is going to go here. And I want H naught, and that's going to be mu equals 32. So go to the Greek letters, do mu equals 32. And I want to prove that it's less than. So mu less than 32. And if I go back here, can you see equal to, less than? That's where this test statistic lives, and that's the p-value. And they only want the answer to 4 decimal places, so let's be neat. And they only want this answer to 2 decimal places, so let's be neat. And I'll do a submit. We good? All fits. Now, on the basis of this p-value, would you agree that 0.0000 is less than 0.5? And when it's less than 0.5, you reject the null hypothesis and you do it because its p-value is smaller, less than 0.5. And in English, we can conclude that the average tire pressure is too little, right? Is less. And let's do a submit answer on that. And everybody's happy. That I would call a pretty standard hypothesis test, right? The only thing is going to be the story. Won't the story change? Next time it'll be about people's weight or reduced blood pressure or whatever it might be, but there's still going to be a mean of a sample size, an H naught. I'm trying to prove it's bigger than that guy, less than that guy, or not equal to that guy. Okay, next story then. Cell phone company. the mean length of calls of all its customers is 9.4 minutes. Okay, so I'm just going to stop right on that sentence because that tells me that mu is 9.4.
Yeah, I had a hard time with that because on the bottom it says it changes.
Well,
So I,
we'll keep it as 9.4 until we'll see, you know, what the issue you had later on.
no, that's what I
Now,
finally figured out is that it was
Oh.
the original mean.
okay, gotcha.
calls.
So you figured it out.
Mhm.
So this company is thinking about offering a senior discount to new customers, but it's only going to do it if the mean length of calls for the customer for seniors is lower than the general customer pool. So basically they're figuring out we can get more senior people as long as we know that when we get senior people, they don't use the phone as much, right? Okay. Financial reasons for that, I suppose. The one way to identify seniors is to conduct a survey and ask people whether they are over 65 and hope they tell the truth. Using this method, the company contacted a random sample of 100 seniors and recorded the length of their last call. Okay, and the mean sample, here we go, and standard deviation, right? So basically in that sentence, N is 100, my sample size. The mean length of call is 8.2 minutes and the standard deviation was 10 minutes. So I've got pretty much everything that I want. So we are trying to prove, our hypothesis is, that seniors have a mean length that's less than 9.4 minutes, which seems reasonable. Would you agree? 8.2 minutes, they do tend to be on the phone a shorter time. Now, that number and that number are going to come from salt. So I'm going to close that one off. I'm going to hit salt. One sample. The sample mean for these people was 8.2. The standard deviation was 10 minutes. And there was 100 people in the sample. So that's where those numbers that I wrote down came from. The guy that goes here, I forgot to write that number down, so it was 9.4. And we are trying to prove that it's less than. Okay, so generate results. This T statistic is this number. And the p-value ends up being that number. And do they have any accuracy mentioned? Nothing there, so I'll just leave the whole thing. 4 decimal places. There you go. That's strange. You would have thought they would have gave that one. Oh, maybe, no, they don't mention any accuracy. Oh, well. Now, conclusion time. Would you agree that that p-value is bigger than 0.05? And when it's bigger, you do not reject. We say fail to reject. Now you fail to reject H naught, and you fail to reject it because of what reason?
There's not sufficient evidence.
Yes. So there's one. It's just one of the many ways that they phrase it. Right? Now, use your results to make a recommendation to the cell phone company about whether or not to do it. Based on these results, the company should not offer a senior discount because we haven't proved it's worth it, right? Because we never found evidence that they actually talk less than anyone else does. Are we good? Right, so let's look at this thing. In the original situation where 100 seniors were surveyed, the test statistic was found to be that number, and the p-value happens to be that number. Yeah. Do you know, if I'd read that, couldn't I have just wrote the answers here and here? Yeah. That's weird, but anyway. Compare the results to the test for the sample of size 100 with the results for the sample size of 400. So what we're going to do now is go back to here and pretend that we got the same results, but from 400, right? So everything else is the same, right? Same average, same standard deviation, same everything. One change, 400 people. Do you think that the T and the P value are going to change because I'm now using a bigger sample? Yeah, and they should change. Well, let's see what they change into. Oh, look what they changed into. In particular, look at the p-value. Isn't that very small? 0.008. So keep that in your mind. In the situation where 100 seniors were surveyed, it was reasonable. Get it this way. It was reasonable. God, it's double negatives. It was reasonable to reject the null hypothesis. It was not reasonable to reject it. That's the right way around. God, the English language. So it was not reasonable to reject the null, right? That's what we said there. Don't reject it. But in the situation where it's 400, it was reasonable. Thus, using a large sample did make a difference. Okay. Pretty sure I got the sentence the right way around. The first one was a bit tricky in my head because was not reject something kind of threw me.
Professor?
Yes.
In part A, it's actually asking for 400 seniors in the sample, so the answers for 100 is incorrect.
Oh. Why did I think it was, oh, I did this with 100? Oh, okay. Can you pretend I did the question correctly then? Because I don't want to go through the whole thing. The two numbers we got are exactly correct. I just got the 100 and not the 4. If you switch places, everything comes out good. And the conclusions come out good. Let's skip 15. Let's look at 16 then. The average height of children who are 2 years old is 34 inches. Okay. A random sample of 35 children who are 2 years old in a large daycare franchise is collected. And they found that the average height of those 2-year-olds was 30 inches. And that the standard, write that down. So it was 30 inches. The standard deviation was 1.7. The new naught is that it should be 34. And we're trying to prove, is there evidence that it's less than 34? And we did it with a sample of 35 kids. So everything I want is here, right? That number there would have been H naught would be mu equals 34, and the alternate would be mu less than 34. We're going to plug that in and come up with a T and a P. So close that one off. In we go. We got a sample mean of 30. We got a standard deviation of 1.7. We had a sample of just 35. The hypothesis would be that it was 34, nothing different, and we're trying to prove that it's less than. So that's basically, in essence, what that story is about. It should be 34, but we tested it on 35 kids at a daycare, and we found it was these numbers that we got. And so we think this is evidence to prove that it's not 34, that it's less than 34. And whoa, that is one very interesting T guy. And the p-value right next door to it is one of those guys. And to 4 decimal places, it's a lot of zeros. And to 2 decimal places, you got that guy. Now, what's your conclusion? Well, would you agree that that is definitely less than 0.5? And when it's definitely less, isn't one of the many sentences if you reject the null hypothesis? Agreed? Let's submit it. Am I good or am I good? There we got it. 3 in a row. Got that one right. Oh, let's look at this data. So in the big population, a 2-year-old's about 34 inches, right? Give or take a few, right? Some are tall, some are shorter, but about 34 inches. Kids in a daycare center are only 30 inches. Let's assume that that's true. The next step would be why, right? Why would children who go to a daycare be a little bit smaller than just the general population of 2-year-olds? Hi, chuck it out there. Give me a reason.
Well, it could be the location of the daycare. Is it a
An economically
yes,
stressed area?
like is it a poverty area? Is it
Right.
or
Okay, stop there. That's
does the
a good one.
daycare offer food for the children while they're at the daycare? It could be a lot. I'm not sure.
Right. So if we just took your first one, if this daycare was one that was subsidized by the government, right? So that in a poorer area, I'm not insulting anyone here. I probably am, but I'm trying to think of a lawyer way of saying this. One of the features of being in a poor area is that people who don't have a lot of money don't starve their kids, but they might not be able to feed them with the right amount of protein and the right amount of good carbs and fresh veg and all the other things that cost an absolute arm and a leg. And so they do very often tend to be smaller. I mean, if you look at poor countries in the world, right, they tend to be smaller in size. And that's a fact of, one of the factors at least, is how much food they have to eat, especially when they're young, right? If you don't, if you get lots of food, maybe too much in America, but if you get lots of food, you tend to grow taller, right? Your body uses it, it turns it into bone, muscle, height, boom, off you go. Now, there's a lot of things to do with genetics. Some people are genetically just smaller than others, but that's true. America is one of the tallest countries in the world. Back home in Scotland, I was about average height. I'm 5'6", which is not tall, but I'm about average. If walking about in the street in Scotland, you wouldn't notice me. I would be right in the middle, right? A couple of people bigger, a couple of people smaller. You come to America, it's like somebody chucked 4 inches onto everybody. You're just that 2, 3, 4 inches taller. And that's a lifestyle, and that's a food thing. I think that'd be a really good reason. I like that one, Cheyenne. You'd have to go into more detail. So if you wanted to prove that, what you might want to do is 2 groups. Couldn't you get a childcare government subsidized place in a poor area and then go to Beverly Hills or some really extortionately expensive place where there was a private, daycare, and look at the heights? And the only difference between those two groups of kids wasn't it the wealth of their parents. right? They're just kids, right? Kids are kids. And so if there was a noticeable difference between those two groups, wouldn't that verify what Cheyenne was saying? Look, good thing to do. Okay, I like that question. It got me thinking. Are you looking at question 17 now? Okay, so in this story, we have a lot of data. Everything we need is in the table. Most of it, at least, is in the table. And in this, it has been hypothesized that the mean pulse rate for college students is about 71 beats per minute. So you have told us H naught mu is 71. Gotcha. A sample of university students recorded their gender identity and their pulse rate. So here are the female data, and here is the male data, and two different sizes, different means, so on and so forth. Right. Interesting. Assume that these samples are representative of all the male and female students at our university. Okay, I can do that. Find the test statistic for testing whether or not the pulse rate of all male students have a mean of 71. Okay, and what are we comparing it against? Well, let's have a look at the males. Right. Okay, I got the numbers. For the males, it's going to be 30. Looking at the wrong one again. For the males, the sample size is 56. The mean is 70.52, and the standard deviation is 9.75. And this phrase here is important. Whether or not it's 71. What do you think the alternate hypothesis is if you want to test whether or not it's 71? That's a funny way of saying it, but what is it? Is it bigger than 71? Is it less than 71? Or is it a not equals to 71? What do you think that phrase is getting at?
Not equals.
Not equal, right? Whether or not, right? It doesn't say, is it bigger, is it less? Now we can look at it and say, yeah, it looks like it's pretty close to being less, but we're being asked to test this one. So now I'm ready to hit the salt button and do the males. And in the males, the mean was 70.52. The standard deviation was 9.75. And the sample size was 56. And this fella was 71. And we're testing whether or not, so that's a not equals to. And I'll generate the results. And here is the T statistic, which isn't that interesting. And here is the p-value, which is not that interesting either. And what did we want? 2 decimal places, so I'll make that 37. And 4 decimal places, 1, 2, 3, 4. That 9 goes up to a 0, so that's going to be 40. Okay. Now, is this p-value? Let me check that. Wow, that is very boring. Would you agree this p-value is definitely not less than that one? So we're going to do the fail to reject. And we're going to pick the insufficient evidence one, right? So there wasn't enough data to show that the males were different from 71. And then they just basically start all over again, but this time they do it with the female students. So for the female students,
I actually did it for the male students with my
data.
with my data, and I still got it wrong.
Well, let me hit the button on that and see that I've got mine right, in case I've misread that. No, mine is right. We can have a look at that sometime, maybe during the office hour, and just go through it. It looks good. Worked here, right? Okay, so let's do it for the female. We'll try it now with the female, right? As I'm doing it, you do yours with your female and see if it works this time. So for the females, there are 34 of them. Their mean is 76.8 and their standard deviation is 11.5. That one might work. Right, so I'm going to try that one. Use salt. We'll make this mean 34. And standard deviation 11.5. And the sample size, oops, got them mixed up. This guy is 76.8. And it's the sample size that was 34. And this is still going to be 71. And we're still trying to prove it's not equal to, so I'll generate the results. That's much more interesting. A T statistic for the females goes here. And the p-value, which is nice and small, which is what we like to see, goes here. And 2 decimal places, you get 94. And 4 decimal places, 1, 2, 3, 4, you get that guy. Now, this fella is less than 0.05, so we do reject H0, and there is significant evidence. So let me try submitting that one. Worked. Did you get the female one to work, Cheyenne? Can't hear you, Cheyenne. If you're talking, you must have.
Yes, I got the female one. It must have been an error. I'll redo the male one.
Yeah, it's easy done. You know how like I got the mean and the number switched around, but I caught it in time. See, if I hadn't caught it in time, I would have probably got the wrong answer as well. Things like that can happen quite easily. Now, then goes on and writes write a few sentences about what's happening here. Well, essentially what that is telling me is that there's enough evidence to show that females do not have a heart rate of 71 on average. But in the males, we couldn't prove it one way or the other, right? We didn't have enough evidence. Interesting. So write a few sentences. The data do not provide evidence that the male's pulse rate students is different from, I think it was 71 in our case. And the data, that's bad grammar, right? But the data provides sufficient evidence that female students differ from 71. Okay. Oh, that's an interesting question. Is the hypothesis test for this situation one in which a decision leading to an action is required? So let's see the choices. No, the hypothesis proves similar results for male and females. No, the results of these hypotheses are simply providing information. That's the one I would go for. I don't really know what you could do about it unless it was dangerous. So let's see if I'm right. They agree with me. And that is everything from the first section done. And I am getting really good at timing because it's 11:50. So last name and bye-bye.